constant. Here we call it K, here we call it G. Here we're multiplying two charges together. In the gravitational force, we're multiplying two masses together. We're still dividing by r squared in both cases, and they both produce forces. But one's a Coulombic charge force, and the other one is a gravitational force. The other interesting thing is here, mass is always negative, so the gravitational force is always attractive. Whereas the Coulombic force can be attractive, but it can also repel. So there's a lot of similarities here, but a lot of differences. As a matter of fact, the form of this equation, when early researchers started looking at this, the form of this equation was guided primarily by Newton's gravitational law. They thought, I wonder if essentially the Coulombic force will have a similar form, 1 over r squared, like the gravity force. And when they did a lot of experimenting, it turned out to be that way. And what's interesting is that there's a lot of symmetry, if you will, in the mathematical forms of these relations. Is there any reason why this has to be exactly 2? Is there any reason why, like r squared, what if it were 2.001? Would that make a difference? Well, actually, it would make a profound difference. If this number were anything other than 2, it turns out, I'm going to erase this right now. We're going to talk about this later, but it turns out if this number in the, this is not covered in the book, but if this number here, r squared, were anything other than 2, suppose it were 2.0000001 or 1.9999998. Or if it were just a little bit different from 2, it would have profound ramifications for all of physics. It would basically mean, if this were to happen, it would basically mean that the mass of a photon, which is the light that the mass of the light is what a photon carries light. A photon is a little pack, a quanta of light energy. It would mean that the rest, what we call the rest mass of a photon, well, right now we know the rest mass of a photon is 0. It would mean that it's not 0. It would have profound implications for all of physics. And believe me, this has been experimentally verified to very high degree. And this is last time I saw is 2.000, and it goes on for about 30 digits. So to the limits of accuracy that we have available to us, or the scientists have available to us, this is exactly 2, to the limits of accuracy they have. Again, if it were not 2, it would change a lot of physics dealing with electromagnetic wave propagation. All right. Let's see. Now we're going to flip over to page 434, and we're going to look at an example problem. Most of the chapter now is going to be dealing with how do we apply Coulomb's law. If we look at the example on page 435, example 13.2. Okay, we have in the center, or about the center, we have minus 3.4 millicoulombs. A millicoulomb, for instance, 3.2 millicoulombs is 0.0032 because coulombs, because a milli, remember, is 10 to the minus 3. Okay, we have a plus 1.2 millicoulomb charge over here, and we have a minus 4.1 millicoulomb charge over here. And separation distance, this is 2.0 meters from here to here. And this is 1.2 meters from here to here. Okay, and the question is, these are the, we have a plus charge, a minus charge, and another minus charge. So the question is, what is the total instantaneous electrostatic force exerted right here on this guy right here? So what is the force on this charge? That's the question. Okay. So, if you just think about it, this is a minus charge, this is a plus charge. There's going to be an attractive force coming this way. We'll call that F1. Okay. And then look here. There's a minus charge and a minus charge here. There's going to be a repulsion force here, repelling force here, and I'm going to put another, I'm going to put it on this way. The force over on this side from this charge is going to push, is going to cause a force to the left. This charge, F1, is going to cause a force also to the left. So the net charge the net force is equal to all the sum of the forces. Now will be F1 minus F1 plus F2. And it will be, remember all forces are vectors. Okay. So how do we figure out what F1? F1, again, is K times Q1, Q2 divided by R squared. In this case, I'm going to call this R1. So this would be R1 squared. I'm going to call this charge Q1, Q2, and Q3. Okay, so we would just put the charges in. K is 9 times 10 to the 9th. I'll leave the units off for now. We have Q1 is plus 0.0012 coulombs. Charge 2 is minus 0.0034 coulombs. Divided by R squared, 1.2 meters squared. And if I take my calculator, okay, 9 e to the 9th times 0.0012 times 0.0034 divided by 1.2, and I square that, and I get, I'm going to write it right here, 25,500 newtons, and it's going, the overall force is negative, but that's really just the orientation or direction of it. It's going to the left. Okay, F2 is the exact same formula, KQ2 times Q3 divided by R2 squared. So that's 9 times 10 to the 9th. Q2 is minus 0.0034. Q3 is 0.0041 coulombs, and divided that by 2 meters. And I multiply that out 9 e to the 9th, whoops, times 0.0034 times 0.0041 divided by 2 squared, which is 4, and I get 31,365 newtons. And again, it's to the left. Now, I will worry about significant figures when I add them. So, the sum of these will be 25,500 plus 31,365. When I add them up, I'm just going to simply add them up this way. I get 5, 6, 8, 6, 5. So, or if I round up, I'm going to just say here the net force, if I go to two significant figures, will be 557 times 10 to the third newtons, and it's directed to the left. Okay? And I could write that 5.7 times 10 to the fourth. Notice that both of them have a minus sign, but again, the minus only indicates the direction. The direction. So you really have to keep track of the signs yourself and know what plus or minus sign means which direction. Okay. So this is an example of how you use Coulomb's law. In this case, you have three charges, and we're interested in knowing what is the net force. The net force right on this middle charge, Q2. Now notice, if these charges were free to move, suppose this was fixed, and this was fixed, this charge is fixed, but this charge was free to move. What will happen? I let it go, there's a big charge heading this way. The charge starts to move. As soon as the charge moves, these forces are going to change, aren't they? Because the forces depend on the radiuses. This radius is going to get smaller. This radius is going to get larger. So what's going to be the net effect on the net force? Well, I don't know. We'd have to calculate it. That's not part of the problem. But you can see that in the force we calculated right here, 5.7 times 10 to the fourth newtons, that is the correct force, but it's only the force right when these two radiuses, R1 and R2, are exactly these numbers. As soon as what we call the instantaneous force, as soon as the charge starts to move, the radiuses move, and we have to calculate a new force. Okay. All right. So that's the problem. Example 13.2 on page 435. Okay. The next problem. The next problem I'm going to do is I'm only going to set it up. I'm not going to solve it. But if you look on page 436, suppose you had an arrangement. Now, and there are problems like this in the homework and on the test, by the way. So suppose you had this kind of arrangement, and this is on page 436. You had, let's see, plus 4 coulombs. Plus 6 coulombs, plus 4 coulombs, and over here you had minus 2 coulombs. Okay, so we'll call that Q1, Q2, and Q3, and the distance from here to here is 0.34 meters. Distance from here to here is 0.34 meters. And this angle here, this is a 45-degree angle. Okay? So this distance here, from here to here, is 0.48 meters. Well, and you think about it, let's check this. since this is a 45-degree angle, this, essentially what we're saying is this 0.34, that's a 45-degree angle. This should be, well, let's figure out what that is. 0.34 squared plus 0.34 squared. Use the Pythagorean theorem, which we can use. 0.34 squared, and we have two of them. Take the square root, and we do get 0.48. So this is quite correct, and we can. So that's just using Pythagorean's theorem. Okay. So the question is this is the configuration on page 437. Oops. The question is, the three charges are arranged like this in this triangular configuration. What is the instantaneous charge on right here? For the Q1, what is the force on Q1? What is that force? We'll call Q1. Well, now, again, we have two charges, or two forces. We have a force this way and a force from here to here. The first force, we'll call force 1. This is a plus charge, this is a plus charge. These two are going to repel each other. So, there will be a force, I'll draw it this way, that will be force number 1. Okay, and again, force number 1 is going to be K Q1 Q2 divided by R1 squared, where this is R1. Okay, and that force is directed straight up. Okay. Now there's also a force this way. Now this is attractive. These plus charge and minus charge, these are attractive, and so there'll be a force directed this way. Also, that will be force 2. Okay, so force 2 which is oriented like this, I'll just say, is K times Q1 times Q3 divided by R2 squared. And I'm going to call this R2. Okay, notice that we have this dimension here, but we're not using it. The problem did not say what's the force between these two charges. Certainly they'll have a force between them, but we're not worried about that. We're only worried about the net force on this on this right here. Okay, so notice that this is a 45-degree angle also. Okay, so from a vector diagram, what we have is we have force 1, we'll call it F1, and it's directly up. We have force 2, okay, at a 45-degree angle. That's force 2. So the net force, notice, what is the net force? The net force from a vector point of view is like this. Okay. So we can draw it, we can diagram it this way. Okay. Now, when they wanted to solve, when they want us to solve it, basically what I'm not going to solve it, but I'm just going to set you up as to how you would do it. Okay. What you want to do is you want to break this force up into its components. Notice the force number 1 is purely, this is a purely y force, so it's purely in one dimension, in the up dimension. Okay, so you would calculate F1, okay, then you would calculate force 2. Okay. Now the force 2 is the one that is oriented at an angle, so that's the one that we can break up into an x and y component. So notice, if that's, we calculate F2, we plug in the numbers, just like we did before, but we break that up into two components. Okay, we break it up into F2x and F2y. Okay, and it's a 45-degree angle here. So basically, F2x will be F2. Here's F2. Okay, in this case, this is F2 in the x component is going to be 40. This main F2 times the sine of 45 degrees. Okay, and the F2 in the y dimension is going to be F2 times the cosine of this 45. Okay. Now, this is how I would tend to do it, and this is going to be a plus because it's going to be oriented to the right, and I know that this is going to be a negative sign because it's oriented down. Now, for those of you who would rather do it the other way, that is the way maybe it was done in the book. If we have this, if that's a 45-degree angle, then from here to all the way around here, what would that be? It'd be 360 minus 45, which is, what is that, 315? It's 360 minus 40 is 360 minus 40 is 220 minus another 5 is 315. So it would be the exact same thing as saying, I'm going to erase it for a second, as saying F2 times the sine, whoops, that's F2, and that's the theta, which is 315 degrees. Okay, that's the same thing as saying sine, cosine of 315, okay, or F2 times the sine of 315. Okay, now if you take out your calculator, what I'm going to show you, the sine of 45 degrees is 0.707. That's the sine of 45 degrees. The cosine of 315, punch in 315 and take cosine, is also 0.707. So I get the exact same number. Okay, so this equals this. Now, if I take the cosine of 45 degrees, I'm actually going to get the exact same number. Now remember, I have a negative sign here. I know there's going to be a negative sign. Now if I take 315 and take the sine of that, I'm going to get a negative 0.707. So, in fact, you can actually do this problem the way the book does it, where they take the angle all the way from the x plus axis all the way around, and you would do it this way. Or you can also do it my way, which is the way I tend to do it, is where you just look at it using angles that are smaller than 90 degrees. And you just know what quadrant you're in. So, in any case, once you get this, okay, I'm going to erase this momentarily, well, right now. Once you calculate F1 and F2, notice F1 is purely in the up direction. So the net y is going to be F1, because that's purely going up. Okay, and we have to add to that F2y, which is actually a force going down. We have to add those together, and then the net in the x dimension, there is no F1, so it's purely equal to F2x. And once we find out those, then the net force is simply using the quadratic equation of these quads, the Pythagorean's theorem. we take the two components, we square them, and you take the square root, okay? And the angle is simply the exact same thing. If you take the tangent of, it would be the F net y divided by the F net x. Okay, the y divided by x, and in inverse tangent. So basically we have the f of x one way, and the f, this is going down, f of y, and we know that the resultant is going to be in the fourth, we know it's going to be in the fourth quadrant, like that. Okay. So, so that's over. I'm not going to actually work. You can work out the problems, and the answer's right in the book. But this is in general how you would do it. So you're adding up forces using their x, y components, and you've done that many times before in previous chapters. The only difference is now you're using the Coulombic force. Okay, I'm going to erase this now. So really, there's no difference in how we add forces. We still have to add forces. The forces, Coulombic forces, are still vectors. We still add them up in 1 or 2 dimensions, just like we add up other forces in 1 or 2 dimensions. We have to break them up. If we have a 2-dimensional problem, we have to break them up into their individual components. We add up all the x's, we add up all the y's, and then we use Pythagorean's theorem to find the resultant, and then we can find the angle just by using the tangent of the angle. And so there's really no difference. Okay, I'm flipped over to page 439. And it's at this point we're going to start talking about the electric field. Okay. The electric field, there's 2 ways. And we'll talk about this more and more. But there's, as we get into the magnetic force and the electric force, when we talk about a force. And we've used this some with gravity, but we haven't done a lot with it, with the idea of a gravitational. We've talked about the gravitational field. And what is a gravitational field? We've talked about what that is. If you're near the Earth, you always feel a pull of gravity. So the field is a function. It's basically a force function that you feel in all of space all around the Earth, for example. Well, the same thing is true for charge. The field is the xyz, a function all hovering around the charge that describes the force. For instance, if we have a plus charge right here, and this is right on page 439, if we have a plus charge, we define the electric field as, we'll call it E, the electric field, and it is a vector. It's a vector quantity, just like a force is a vector quantity. It's the force divided by a charge. In this case, what I'm going to say, this charge here is a little test charge. And I'm going to describe exactly what that means in a second. First of all, suppose I have a plus charge right here. I'm going to put plus big Q to separate it from a little q. 2 charges, one I'm just going to call it big Q and a little q. Okay. By definition, we say that the electric charge, the electric field, we call it electric field lines. The electric field lines come out of a plus charge and go into a negative charge. And this is purely by convention. In other words, and this really goes all the way back to people like Benjamin Franklin in the 1700s, who started doing experimenting. They knew there were two kinds of charges. They had to call them something, so they called them plus charge and minus charge. And they knew that they created, there was this idea of an electric field, and they had to come up with a convention. And the convention they came up with was that the electric field lines come out of a plus charge, and if there were a negative charge here, they would go into the negative charge. Okay, so the electric field, what are called electric field lines, are lines of where the actual force field goes. Okay, we'll describe it as we go along. If there is no charge, if all there is around this plus charge is air or vacuum, there's no negative charges anywhere around, these electric field lines radiate out radially